Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at some examples of combining the different derivative rules with functions that have fractional exponents. So again, you should be familiar with these rules. You should be practiced in finding the derivative using the product rule, quotient rule, and the power rule, because in this video we're going to be combining all of those. I talked about this in the last video and we did some examples of combining these three rules, and make sure you take a look at those types of questions first, because we're going to be doing more of the same, just a little bit more complex. So let's get started. So my first example is a product. Here's a function, polynomial function, and then here's a power function, and my exponent is 1/2. So I know that I'm going to have to use my product rule. I have a function times a function. So remember what your product rule is, and then identify the u, which is 3x cubed. Find the derivative of that, 9x squared. Define v, x squared minus 4 to the 1/2. And by the way, you can't take the square root of each term. I've seen students do that numerous times. It doesn't work. But we can differentiate this according to my power rule. So the derivative would be equal to n, which is 1/2, times the function to n minus 1. So 1/2 minus 1 is negative 1/2. Then don't forget the chain rule. You want to multiply by the derivative of what's inside. So the derivative of x squared is 2x. Minus the derivative of 4 is 0. Then I would clean this up. 1/2 times 2x is just x times this. So there's the derivative part. We plug these into our formula. So the derivative will equal u, which is 3x cubed, times v prime, which is x, times x squared minus 4 to the negative 1/2. Plus v, which is x squared minus 4 to the 1/2, times u prime, which is 9x squared. So that is typically not, once students have this figured out, plugging into the formula is not too bad. Where I see students have difficulty is trying to simplify this, and there's two ways we can approach it. First of all, I might clean it up, combine these, so that's 3x to the 4th. And I can do one of two things. I can leave this as a negative exponent, and then I can factor out my largest factors out of both terms. But it gets more difficult when you have a negative exponent. The other option is just to clean up each term independently. So this would be 3x to the 4th. And then I'm going to move this to the denominator. So it would be x squared minus 4 to the 1/2. Plus, this would be 9x squared times x squared minus 4 to the positive 1/2. And usually you're going to be expected to combine these terms. So in order to do that, we need a common denominator. This doesn't have a denominator, so the denominator is 1. So I need an equivalent fraction to this, but with this as the denominator. This is my lowest common denominator. So I'm going to multiply the denominator by x squared minus 4 to the 1/2. And whatever I multiply the denominator by, I multiply the numerator by the same thing. So I haven't changed the value of the fraction because I've just really multiplied by a value of 1. Now, when I do that, I'm going to end up, I can multiply these two powers because they have the same base. So I'll have x squared minus 4 to the power of 1 over x squared minus 4 to the 1/2. Now that I have a common denominator, I can combine those numerators. So that will be 3x to the 4th plus 9x to the 4th minus 36x squared all over this denominator. I can combine my like terms. I'll have 12 x to the fourth minus 36x squared I can leave it like that, or I could factor a 12x squared out, and I'll be left with x squared minus 3 over x squared minus 4 to the 1/2. So either option would be acceptable for simplification. So you either are going to have to work with factoring and work with negative exponents, or you're going to have to work with fractions. So both are challenging, but those are your only two options. Let's take a look at using these same functions and doing a quotient. So in our next example, I use the same function for u. So the u prime is the same. I use the same function for v, and therefore v prime is the same. But I took a quotient of those two functions rather than a product. So now we have to use the quotient rule, which is outlined here. I'm going to take these values and plug into this formula. So the derivative will be equal to v, which is x squared minus 4 to the 1/2, times u prime, which is 9x squared, minus u, which is 3x cubed, times v prime, which is x times x squared minus 4 to the negative 1/2, all over the denominator, or v squared. So I'm just going to clean this up a little bit. And instead of showing you both methods, the way you can do it by factoring or fractions, I'm just going to stick with fractions because I think that most people will have less difficulty with that method. So I've got x squared minus 4 to the 1/2 times 9x squared. 3x cubed times x will be 3x to the 4th. And then I'm going to write this in the denominator of that term, so it will have a positive exponent. When I have a power raised to another exponent, I simply multiply the exponents. So I will have x squared minus 4 to the power of 1. This is not considered simplified, but I did talk about a shortcut that you could use in simplifying, a complex fraction such as this. And that shortcut is you just multiply numerator and denominator by any denominators in any terms. So we're going to multiply by this, which is our lowest common denominator. And whatever I do to the numerator, I have to do the same thing to the denominator. Now, when I multiply this to the numerator, I have to multiply to every term. So I multiply to that, and I multiply to this. But it'll clean up really nicely. Just watch. So when I multiply this term by this, I will have 9x squared times x squared minus 4 to the power of 1/2 plus 1/2 is 1. Then when I multiply this term by this, it will cancel, and I will just have minus 3x to the 4th. So that's how beautifully the numerator cleans up. Then the denominator, this is like to the power of 1. So when I multiply these powers with the same base, I have to add the exponents. So that will be x squared minus 4 to the 3/2, and don't even think about canceling. I talked about that in a previous video. That is a factor of a term. It's not a factor of the whole numerator. You cannot cancel. But I can clean this up a little bit. That's going to be 9x to the 4th minus 36x squared minus 3x to the 4th over that denominator. And I don't have room, so I'm just going to take 9x to the 4th minus 3x to the 4th and get 6x to the 4th. If you wanted, you could factor out a 6x squared. So I will be left with x squared minus 6 Both are considered simplified. The only reason factoring would be desirable is if it allowed you to simplify by canceling common factors. There wasn't anything that I could cancel because of that, so this is just as good as this, or this is just as good as that. Okay? Let's take a look at one more example. In this next example, we have a power, and inside the power we have a quotient. So instead of using the quotient rule initially, I'm going to use the power rule, and then when I go inside of the function to find the derivative of what's inside, then I need to use the quotient rule. So let's take a look. I would use the power rule and say the derivative is n, which is 3, times this function to the n minus 1. And then remember, according to the chain rule or the power rule, I have to now take the derivative of this. This is a quotient, so I need to use my quotient rule. So v is 2x plus 5 times u prime, so the derivative of 3x minus 1, which is 3, minus u, which is 3x minus 1, times the derivative of v, the derivative of this polynomial is 2, all over v squared, so the denominator squared, so that is one way we could approach this question. We could treat it as a power first, and inside the power we have a quotient, so we have to use the quotient rule when we find the derivative. Let's just clean this up. Now at this point, what I would like to do is I'm going to break this up as 3x minus 1 squared over 2x plus 5 squared. My laws of exponents allows me to do that. That way I'm going to be able to work with those factors. Now I will clean up all of this, so I'm going to have 6x plus 15 minus 6x, minus minus gives me plus 2, all over 2x plus 5 squared. And here 6x minus 6x is gone, so we're going to just have 17. 15 plus 2 is 17, which I could multiply to the 3. So that would be 51, 3x minus 1 squared, all over 2x plus 5 to the power, if we add our exponents when we're multiplying powers with the same base, 4. So that's one way we could approach that question. The other option is we could have broken this up using our laws of exponents to that over this. And then I would treat it as a quotient first, and inside the quotient, the numerator is a power, the denominator is a power. So you can approach it either way. I think this is probably the easiest way, the way we did it, but you can try it like this, and now it's similar to, an example we did previously. So practice these. You want to get good at a variety, a combination of different rules in finding derivatives, because you're going to see them, and we're just going to be learning more rules in a little bit later. Right now we're just working with algebraic functions, but we are going to look at non-algebraic functions in a future video. So practice these, come back to these examples if you get stuck, and don't stop too early. You've got to make sure that you simplify so that if you do have fractions, you express it as one fraction. All right, in the next video, I'm going to start talking about implicit differentiation. So once you're ready, we'll see you then.